All right, so on to the triangles and semicircles assignment. So some interesting things that's going to happen in this assignment is, well, the fact that technically this is an implicit relation. It's not a function. And if you remember, we were dealing with these equations that had two functions, f and g. So that's going to make our work a little bit more interesting. Let's see what the problem says. It says we have cross sections perpendicular to the x-axis, so this is a regular dx integral, and those cross sections are isosceles triangles with the hypotenuse as the base, aka this formula that we derived earlier. So again, we don't have an f and a g function, but we'll find a way to figure out what we're going to do about that. So since this is a dx integral, let's first take that implicit relation and solve for y. So we get plus or minus 16 minus x squared. And so the thing is, we actually do have two functions here. F, or the higher function, is the positive root of this, and g would be the negative root of this. Now, what's special about that is that means the entire base is actually this. The base is simply 2 of those square rooted values. Why is that? Because when you take a positive root, when we take f, the positive function, and subtract g, the negative root, you're going to double negate and get 2 of those roots. Okay, so with that being said, now let's kind of take a look at this formula here. If our base is 2 of those square roots, then our formula says that an area of an isosceles triangle is 1/2 times that base times half of that base, because half of that base is the height when you have an isosceles triangle with the hypotenuse as the base, which again we talked about in that previous video. So again, the idea is that means my integral is going to be the integral of 1/2 2 of those bases, or 2 of that function, and then the height, which is half of the base. Okay, so we get a lot of simplification there. Also, let's figure out our bounds of integration. Since that is the equation of a circle, those bounds will be from -4 to +4. And if we clean this up, the 1/2 and the 2 will multiply and cancel out. The root and the root will multiply as well. So really, we just have the integral of -4 to 4, 16 minus x squared dx. So we actually don't have too hard of an integral to compute, but they do want the actual integral. So let's actually integrate that now. That'll be 16x minus x cubed over 3. We need to evaluate that at 4 and -4. There is a trick you could do here just to say that this is an even function. 16 has a power of 0 for the x, and this is a power of 2 for x. When you integrate an even function, instead of integrating from -4 to 4, in other words, instead of having to plug in, get two answers, and subtract them, it turns out that when it's an even function, so integral of, even function, so I'm just going to put that in quotes, from -a to a, you could just do 2 of the integral of 0 to a of that even function. I'm not going to do that here, but one thing I'm going to point out is, why does that make things easier? Well, because notice when we integrate, we would only have to plug in 4. Well, actually, we can kind of take this approach anyways. We plug in 4. When we plug in 0, everything has a variable, so it goes away. So we just have to double what we get from 4. And maybe you'll see why that's true anyways, as we just actually evaluate this thing. When I plug 4 in, that's going to be 64 minus 64 over 3. That's the upper plugged in. Minus, when we plug in the lower, we'll get -64 minus 64 over 3. And so you can kind of see we just get double what the first was, because when this negative distributes through, wait a minute, that would be positive when I cube it. Yeah, so when I distribute the negative, I actually get an exact copy of what I already had. I have 2 of the first evaluation. So just a fun little trick you can do there. But let's see what that's going to be. That's 128 minus 128 over 3. And if I want to kind of work this out, I wonder if it'll take that as 2 expressions. My answer should be a simplified proper fraction, so never mind. Just need one answer. Okay, so I need to multiply that by 3. 384 over 3 minus 128 over 3. And then that would just be 256 over 3. I'm pretty sure. I sure hope. Yay. All right, 3 more. This time we have my setup and do not solve integrals. Not mine, but my favorite, which is set up and do not solve because I don't have any work to do. This one actually is also a little bit interesting because they don't even want me to actually do the integral, they just want me to set it up abstractly. So I don't even know what these functions are. Let's see here, it says cross sections perpendicular to the x-axis. So if I'm perpendicular to the x-axis, that is a dx integral anyways. So that's going to throw out answer choice A because that's a dy integral, and it will also throw out answer choice D. From there, let's think about if these are semicircles. Again, a semicircle is 1/2 pi r squared, but in this case the radius is 1/2 pi r squared, and the radius is, again, 1/2 of the distance between those two functions. All right, well, when I square that 1/2, that will get me 1/4, which will also multiply to a half and get me 1/8. It looks like that's going to be my answer. Also, since it's an x integral, it should be going from a to b. And then there's that pi involved. So the one careful thing to notice there is that that squared, because that 1/2 is multiplying to everything, you can just essentially square that 1/2 and then pull that out as 1/4 times a half to get you that 1/8. But you will have an entire f of x minus g of x squared. You can't just distribute the square because those are subtracting from one another, but since the 1/2 and that whole expression are multiplying, we can quote-unquote distribute the exponent through those multiplying pieces. All right, 2 more. Up next, we've got cross sections perpendicular to the x-axis that are equilateral triangles. So once again, I've got a dx integral, and that means I need to solve that equation for y. It'll be 1 minus x. Remember that 1 minus x this time is just going to be compared to 0, aka the x-axis. There's not actually 2 functions here. And let's just look at that equilateral triangle formula again. That equilateral triangle formula is 1/2 base times height. And again, for reasons we found out before, that height is going to be square root 3 over 2 multiplied to whatever that base distance is. So let's see here. That base distance is 1 minus x, so I've got 1/2 times 1 minus x times square root 3 over 2 of 1 minus x, all in an integral from 0 to 1. So in simplifying that, again, there's that root 3 over 4, and then I've got a 1 minus x squared dx. Now, it's up to you. You can actually, FOIL this out and then integrate it, or you could think about this as a chain rule. I think I'm going to do that in hopes that it might make my life easier. So if I think of this as a chain rule, I know there is a negative that's going to pop out or, be present in my integration. So a negative is going to come out. I still have that root 3 over 4. That exponent is going to increase. And that means I need to offset the 3 that's going to drop down. So this should be a 12. And so that should be actually what we get from the integration. Let's just double check that. Again, if I derive the inside, a negative comes out, -1, so now it becomes positive. A 3 will drop down, so now I just have a 4, and the exponent will decrease, so I have a 2. Yep, that's the right integral. Now let's evaluate it. This time, when I plug in 1, that just gets me a big fat 0, minus -3 over 12 times whatever I get when I plug in 0, which is just 1. So it looks like my answer is just square root 3 over 12. All right, the key here is, if you have these kind of memorized and understand how they're coming about, it's not hard. The hard part is getting there, though. Again, especially if you don't remember that it's root 3 over 4 times that base distance squared, you'll have to re-go through this whole process of drawing a picture, thinking about the 30, 60, 90 relationship. Just, consider memorizing all that. All right, finally, a dy integral that we have to compute. So we've got cross sections perpendicular to the y-axis. So this is a dy integral, and they are semicircles. So I am going to skip and say that we're dealing with pi over 8 f minus g. F of y minus g of y. The question is, how do I get f of y minus g of y? And what are my bounds of integration? Well, my bounds of integration look like they're 0 to 4. And f of y and g of y are actually still, again, going to be related to the same function, actually, because we've got another implicit relation here. So if I square root both sides, I get x equals plus or minus the square root of 8y. And so again, that means what we really have is we have two functions, the positive root of 8y and the negative root of 8y. And so the distance between those two will be simply 2 square root 8y, because it will be the positive minus the negative, which will just end up adding. Okay, so that means 2 root 8y is what goes inside of here. Let's integrate. We've got a pi over 8. We've got a 2 root 8y squared from 0 to 4. And that's a dy integral. So when I square that, that's going to become a 4, which will, do some algebra with that 8. So we haven't actually integrated yet. And then we just have 8y on the inside of the integral. So actually I'm going to pop that 8 out as well. So that's just going to be 4 pi times y dy. So when I integrate that, that'll be y squared over 2. So the over 2 will work with the 4 again. Evaluate that at 0 and 4. I only have to worry about plugging in 4. That looks like that's going to be 32 pi. All right, and there we go. So you're definitely going to see a lot of different types of questions here. Just be careful as you work through them. And I would really take to heart memorizing those formulas for each of those different shapes that you encounter as you integrate. Good luck.